Electric field. In the last unit, we covered electric force, which is an attractive or repulsive force between two charged objects. It can be determined using Coulomb's law here. The electric force is K times one charge times the other charge divided by r squared, which is the distance between them. And the important thing to realize here is we're dealing with magnitudes to find the force. Like the gravitational force, electric force is a non-contact force. This action at a distance is best understood by assuming that each charge has a field surrounding it that affects other charges. The electric field is a region around a charged particle or object within which a force would be exerted on other charged particles or objects. To find the electric field due to one charge, begin with the electric force between two charged objects and assume that one charge is very large and the other is a small positive test charge that really doesn't have much of a field. So the capital Q would be the large charge and the little q is the positive test charge. The electric field, and we'll abbreviate that capital E, due to the larger charge, and that's this big Q here, can be found by dividing the force above by the smaller charge, little q. So we'll get the electric field is equal to kq over r squared. The electric field now shows both the magnitude and direction of the force exerted by Q on any charge. Q creates the electric field. The size of charge Q and the distance from Q determines the strength of the electric field. The units for the electric field are newtons per coulomb, or N/C. The previous slide showed the magnitude of the electric field. So how do we determine its direction? Well, the direction of the electric field is determined by the direction that a positive test charge, small test charge here, would accelerate if placed in the space surrounding a charge Q. What would happen if an isolated positive test charge were placed near a positive charge Q that's generating this big field? And again, we're assuming the test charge doesn't have very much of a field at all. An isolated positive charge Q, plus Q over there, will repel a positive test charge. Therefore, the direction of the electric field surrounding a positive charge points radially outward or away from the positive charge in all directions. So this shows the force on this little positive test charge, and there's our electric field lines, because wherever we put a positive charge, it will move away from the charge generating the field. Now what about a large isolated negative charge over here? Well, that will create an electric field that points radially inward towards the charge in all directions, since a positive test charge will be attracted by negative Q. The definition of the electric field shows that the strength of the field decreases as distance increases. So the force is proportional to the electric field, which is proportional to 1 over r squared. This can be seen by looking at the density of the field lines. The electric field lines are closer together or more dense when they are closer to the charge that is generating the field. This indicates the electric field is greater nearer the charge. And here's a nice simulation from PHET. Michael Faraday created the concept of the electric field. He was born in London in 1791. He came from a poor family. At age 13, he apprenticed as a bookseller and binder while also attending local lectures on philosophical and scientific topics. A member of the Royal Institute took notice of him and bought him tickets to several Royal Institute lectures. In 1813, he was invited to work at the Royal Institute, where he made numerous contributions to physics and chemistry. Let's relate the electric field to the gravitational field now. Given that a mass, little m, is located at the surface of the planet with a mass of large M and radius r, Newton's law of universal gravitation is used to determine the gravitational force between the planet and the little mass m. This looks somewhat familiar, right? Just like Coulomb's law, except Coulomb has a little k in there for the g, and it has charges instead of masses. So we're going to divide this expression by little m. where little m is much smaller than big M, similar to what was done with the small positive test charge Q. And we'll call this G the gravitational field. There are parallels between gravitational force and field and electric force and field. Both are non-contact forces that act along the line connecting objects. The strength of the force decreases as 1 over r squared. The field magnitudes are proportional to the product of the masses or the charges. The key difference: mass, which is the source of the gravitational field, is always positive, and the force is always attractive. Charge, the source of the electric field, can be negative or positive, and the force is either attractive or repulsive. So we have some information about the electric force here and the gravitational force here. The equations are very similar. Mathematically, they look identical. However, the constants are different, and we're dealing with charge on the left, mass on the right. R is the same. It's the distance between either the centers of charge or the centers of mass. And finally, the electric field. Again, the equation looks very similar. Just different letters, different quantities. A 2.40 microcoulomb charge is subject to a 3.00 millinewton force due to an electric field. What is the magnitude of the electric field at the location of the charge? We start with our givens, and the key thing in the beginning is to convert to coulombs. And 1 microcoulomb is 10 to the minus 6 coulombs. And also convert millinewtons to newtons. Right? 1 millinewton is 10 to the minus 3rd newton. We use our definition of the electric field, and we have our force here, we have our charge, we substitute in the givens, and we get an electric field strength of 1,250 newtons per coulomb. What is the direction and magnitude of the electric field due to a minus 6.8 microcoulomb point charge at a distance of 7.4 meters? For our givens, we convert microcoulomb to 10 to the minus 6 coulomb. We use our definition of the electric field, which is kq over r squared, substitute in our givens, and we get an electric field strength of 1.1 times 10 to the 3rd newtons per coulomb. Now, we started with a negative charge, but don't use that in calculating the magnitude of the electric field. However, what you do use is it's a negative charge, so the electric field lines point towards the charge as indicated right here.